then we could be shadows to a higher dimension on the edge of the event horizon that they observe. And so it's been called a holographic.
Some scientists are seriously exploring the idea that we live in a huge three-dimensional holographic universe.
The holographic principle is the idea that the physical reality that we are familiar with in this 3D environment that we can readily access with our eyes and our equipment, this 3D reality might be sort of like a holographic projection of more fundamental information and laws that exist and operate on a thin two-dimensional surface that bounds us, that surrounds us, perhaps way out on the edge of the observable universe.
This mind-bending concept starts with black holes. These cosmic objects have gravity so intense that not even light can escape. They swallow everything that comes too close. But the real mystery begins when the object crosses the point of no return.
When an object crosses over the edge of a black hole, its event horizon, the object enters a realm basically of empty space, of darkness, and it continues to be dragged toward the center of the black hole, toward what we call the singularity, where it gets crushed out of existence. Every object, in some sense, contains information because it contains a very specific arrangement of particles. So where is the information that describes the arrangement of those particles? Where does it go?
Stephen Hawking's description of this process was that energy remains conserved, but information disappears. But the laws of physics say information can never truly disappear. So where does this information go? This becomes one of the biggest puzzles in science, the black hole information paradox.
This debate furiously went back and forth up through the 80s and into the 90s when people finally began to articulate this new principle, this holographic principle. And what it said is that all the things that were falling inside a black hole were somehow captured in a preserved image at the horizon itself.
In this view, information is never lost. It is preserved on the surface area of a black hole. It was Jacob Bekenstein who first uncovered this deep connection between information and a black hole's surface area. But then Gerard Hooft and Leonard Susskind pushed this further, asking why this rule should be limited to black holes. After decades of research, they provided the mathematical evidence that our entire universe follows this same blueprint.
Yes, that the three-dimensional world is a kind of illusion, and that the ultimate precise reality is the two-dimensional reality at the surface of the universe.
Leonard Susskind and others have built a solid mathematical foundation for the holographic principle of the universe. But in physics, equations alone cannot tell the whole story. Every idea must face the test of experiment. Now scientists are turning to gravitational wave detectors, such as LIGO, to see if space-time is perfectly smooth or if it has tiny quantum irregularities, as holographic models predict. If they succeed, it would be the first experimental glimpse into holographic space-time. The search for the cosmic pixel has truly begun.